Yeah, my name's Jim Harris. I'm a principal software engineer in Intel's data center group and one of the SPDK core maintainers. We started this project about 6 years ago. A few of us kind of had this idea, like maybe we could come up with something new for storage, doing user space, pulled mode drivers, and we got an NVMe driver kind of up and working, and we got nice SCSI target kind of up and working, and then we at Intel, there becomes a stage where your project gets to be big enough and you have to go consult the magic Intel 8-ball and get your code name. And so we hit the jackpot with SPDK. We got Waikiki Beach was our code name. We joked for a long time that maybe once if the project got big, we could do a conference at Waikiki Beach. And now here we are 6 years later. We've got 300 and some people registered. We've got 3 tracks, but we're still not at Waikiki Beach. So I don't know, where's Anu? When can we get this moved to Hawaii? Is she in here? We'll have to talk with her about that. So anyways, want to talk a little bit today just about what's been going on in the SPDK community, some of the features that we've been adding, and then kind of looking forward, what you can expect to see from SPDK over the next year. There's going to be obviously a lot of tracks, so I'm going to spend quite a bit of time today kind of plugging some of the other talks too. Most of what I'm going to talk about over the next 20 to 25 minutes, you're going to see talks on as well. So the first one, we kind of like to look at SPDK and see, where have all of the commits been coming from? And so here you can see 3 different ranges. These roughly translate to a one-year period. That first one was basically 2016. The second one covers 2017, and the last one covers 2018. And I think the biggest call out here is the number of committers and the number of commits that we're having come in from out of Intel, from outside of Intel. One of the things that we really wanted to do early on was we wanted to make this just not an Intel project, but an open source project. And I think we're starting to see this happen a lot more. We had about a 2/3 increase in the number of non-Intel committers, and we've had about a 3x increases for the number of commits that have come in from outside of Intel. And so there's been a lot of companies that have been actively involved. Shuhei Matsumoto from Hitachi, he's one of our SPDK core maintainers. He's been doing a ton of work. We've got people from Oracle, Mellanox, SolarFlare, a lot of other companies that are going to be talking, and a lot of them have been contributing as well. When we kind of look at the community growth, this is just kind of a little bit of a metric for us, like who's going out and checking out SPDK, and so we track this data. We've seen about a 30% year-over-year increase as far as how many people are going out to our GitHub site on a daily basis. And that's up about over 200% since the beginning of 2017. So that's been really good growth as well. I think the thing that people are probably most interested in hearing about today are a lot of the new features that have come into SPDK. Everything here is basically what the project was about this time last year. So this was after our 1804, the April release in 2018. The biggest one, probably over the last year, has been NVMe, the TCP transport. So as NVMe over Fabrics, it's gained a lot of adoption. People are really excited about it. Primarily it was RDMA, Fiber Channel was added, but people really wanted to use this on TCP as well. And so this was ratified by the NVMe working group back in November, and SPDK had a fully functional target and initiator implementation ready to go. Zia Yang, who's back in the room, he had that all ready to go. So the second that the working group ratified that, we were able to get those patches out and people could start using it. And you'll hear Zia and Seth, they'll talk a little bit more about that in a talk tomorrow. One of the other key parts here is we've built a socket abstraction layer in SPDK, basically to be able to plug in alternative TCP stack implementations. So by default, SPDK uses the Linux kernel TCP stack. There's some patches out there to be able to also use the VPP user space stack. This is from a project called Fido, fd.io. And then there's also going to be a talk from SolarFlare. They're going to talk about their OnLoad TCP stack and how they've plugged this into NVMe, the SPDK target as well. So next, crypto. For those who were here last year, Paul Luce did a talk on this. At the time, this was kind of in progress, but this has been fully developed now. So this leverages the DPDK framework. So for those that aren't super familiar with SPDK, we leverage DPDK for a lot of the nuts and bolts of what we need to do with user space pulled mode drivers. So DPDK is for packet processing what SPDK is for storage. And so they've added this framework to be able to provide a common API to do encryption, decryption operations. So it enables us to be able to take advantage of hardware accelerators on systems that have them, for example, Intel Quick Assist, or to be able to use optimized software algorithms from things like ISA-L, where they're hand-coded specifically to take advantage of the latest x86 instruction sets. And so you can get all of that out on SPDK today. So next, on the integration front, Cinder. So, I mean, obviously, if people are picking up SPDK, it needs to be brought into frameworks that are going to take advantage of it. So the orchestration, administration, management parts come into play here. Maciek Shved, who's here, he's going to be doing a talk on this, I think later today, maybe tomorrow morning. He's going to talk about this in a lot more detail. So we've added a driver into Cinder to basically enable doing block provisioning with OpenStack using SPDK. And this was just released in the OpenStack Stein release that I think came out a week or two ago. And so this enables using the SPDK NVMe over Fabrics target, using the logical volumes, and it does all this using the JSON RPC interfaces that we've added into SPDK. So this JSON RPC interface, this is really the kind of the bread and butter for how people should manage and administrate SPDK applications, and Cinder's building on top of that. And then there's some work going on to also extend this into Kubernetes, and I think Maciek's going to talk about that as well tomorrow. So next, Open Channel FTL. I think this is a really neat feature. I think that the industry is definitely moving this way. John Rudelich from Intel and I came up last year and talked about this for a little bit. And this is a case where we've actually made more progress on this front over the last year than we had even thought we would a year ago. So for those that aren't familiar, Open Channel kind of builds on this idea of taking some of the smarts out of the SSD and putting them up on the host system instead. Because a lot of times the host system has a better idea of how to manage that flash. It can get a lot better, a lot tighter latency guarantees, be able to solve some of the noisy neighbor problems. And so what we've done is in SPDK, we've created a host block FTL based on the Open Channel 2.0 specification, and we've integrated that into the SPDK NVMe module. So that's all out there today. There's actually, for those that don't have Open Channel SSDs, it's not something that's readily available right now. There's patches where you can emulate them with QEMU. So we've got that out there too, and that's how we're actually doing a lot of our testing. And then one of the long-term goals is, as the NVMe working group, they're moving, instead of Open Channel, towards a concept called zone namespaces. I'm not going to get into a ton of detail on that, but that seems to be where the industry is kind of moving. And so I think long-term SPDK will be settling on that as the primary interface with adapters to be able to support Open Channel. So you're going to hear a couple of talks. Wojtek Malakowski is going to be talking about the SPDK implementation that's upstreamed. And then you're also going to hear from Circuit Boulevard and Marvell. They're going to talk about some work that they've been doing with SPDK and these flash translation layers as well. So next, OCF cache. So OCF stands for the Open CAS Framework. CAS is a software acceleration, a caching library that Intel has had for several years. And most recently, last quarter of 2018, it was completely open source. So there's a GitHub project out there that has this entire library, and it's been designed and open sourced in a way that it can get plugged into different frameworks like SPDK. And so we have that integrated in SPDK now. We've got a BDEV module so that it'll pull down all the OCF code, it'll integrate it, and then you can do things like, accelerate. Maybe you've got your core backing device is a QLC NAND SSD, and then you can accelerate it with a much smaller, like Optane SSD as the cache. So you can see there's a good demo right outside this door where you can see some more info on that, some nice performance comparisons, and then Jay and Tomac will be doing a talk on this later as well. And then finally, kind of back on the management front, I don't know, this is just kind of a cool feature that I like, what we call the SPDK CLI. It's just kind of a nice little terminal UI to be able to configure SPDK applications. It's kind of neat. It's a little bit easier than using, typing out really long command lines for JSON RPC calls. It's kind of a neat tool. We'd like to see more people using it and giving feedback on it. I think there's more we could do there. Okay, so that's kind of looking back. So looking forward. So, one of the things looking forward is not just features, but also some of the usage models. Like, where do we see SPDK getting adopted? Where do we see people using it down the road? One of those is in, like, rack scale architectures. So Steve Miller is going to be giving a talk later today on some work that Intel's doing to be able to use SPDK as a, I can't call it ephemeral. What am I supposed to call it? Non-durable block storage using SPDK. So he's going to talk a little bit more about that and why they adopted SPDK for that. And then also on the SmartNIC front. So we're seeing more people, we're seeing a lot of people out there. Mellanox has talked about this, and you're actually going to hear Oren and Sasha from Mellanox later today, I think here in the ballroom, talk about this in a little bit more detail, as far as what people are doing with doing some offloads onto SmartNICs and then running SPDK on those SmartNICs to help enable some of those offloads. So it's another really good use case for SPDK where some of the flexibility and deployment, it lends itself really well to that. And then, of course, we've got a number of new SPDK features. One of the ones that I'm personally actually working on right now along with Paul Luce is block level compression. So this kind of gets to one of the nice things of having the PMDK guys here this week, because there's quite a bit of work we're doing here to basically pull SPDK and PMDK persistent memory together. So on the compression side, just like what we talked about with crypto, is DPDK framework also has APIs for doing compression. And so again, we can offload the compression algorithms themselves. SPDK is we're not designing our own compression algorithm. This is basically a metadata format for doing block compression. That's what SPDK is doing here. And so again, you can use accelerators or optimized software to do those compression algorithms. We're using PMDK, so we're using persistent metadata for to basically store all the block metadata. How do we map the compressed blocks to where they are on disk? And this is one of, I think, the cool, people ask a lot, like, well, how do PMDK and SPDK work together? And this is kind of what it is looking at places where we can use persistent memory and PMDK to be able to enable things like block compression, where we've got really small metadata updates. And yeah, you could store those on disk, but man, it's a lot nicer when you can do it with persistent memory when you're only doing 8 or 16 byte metadata updates. And then finally, this pulls in some of the existing SPDK functionality, like thin provisioned logical volumes, and that's basically how we realize the compression savings. So you can create a thin provisioned logical volume. You run this block compression on top of it, so you don't actually allocate all that storage up front. As the compressed blocks get written to disk, it'll get consumed, and it's a really nice way to be able to get that savings. So if you want to hear more about that, Paul and I will be doing a talk on this tomorrow morning. And then finally, IO URing. I know it's kind of a bizarre name. I've heard people have some, other names for it. I'm not sure why they picked that name, but basically stands for IO User Space Ring. So this is something that the Linux kernel has added more recently. What we're seeing is that is SPDK has become more and more broadly adopted. People are familiar with some of the SPDK performance claims. We're actually seeing other software projects like the Linux kernel to start take some of those same concepts and try to make some improvements to try to get a little bit closer to kind of where SPDK has set the bar. So this is right now under development. I think it's actually been merged. It's going to be part of Linux 5.1. And it's huge efficiency improvements compared to Linux AIO, what sort of the standard is today for doing asynchronous I/O with the Linux kernel. I think it's about 2 to 2.5 times more efficient than what Linux AIO does. It's still there's still quite a bit of gap between that and where SPDK is. And there's another demo out here where you can see some of the improvements on the Linux kernel side, and then you can also see some of the improvements we've been making in SPDK as well and where those comparisons are at. Yeah, future work. So I think a big one is smart scheduling. When I say smart scheduling, I mean with these poll mode frameworks, you've got all these cores and they're always polling at 100%, right? And we know that that's not always the most efficient way to use those cores, especially if those cores, you don't need all those cores to hit the workload that you're currently doing. Ben Walker is going to be talking here a little bit later about some of the stuff we're doing in SPDK to make this a little bit more dynamic, being able to move the work that SPDK is doing between cores so that we can either shut cores down or we can even, using some of the Intel technologies like Speed Select, to be able to kind of bump the frequencies up and down based on the workload. So I think that's going to be a really, really nice feature, and Ben's going to talk more about that. Another one is block indirection. So this is kind of taking some of the ideas that we've been doing around the FTL, where you have blocks. The user has said, I want to write this amount of data to this LBA, and we're storing some of that metadata to basically keep track of where those blocks actually are on disk. And we think that there's some other usage models that we can take advantage of here, where that host FTL isn't just for open channel or zone namespaces, but maybe some other cases too, where we want to be able to do very, very large writes to the backing device, and then maybe have a high-speed write cache in front of it to be able to aggregate those writes. Talked a little bit about zone namespaces. This is getting a lot of traction in the NVMe working group. I really think that people are going to look at SPDK as like really the primary way to be able to do innovation in this area. And so we want to make sure with SPDK that we're ready, once that spec becomes public, that SPDK's got APIs and other things in place to enable that. We got replication and parity. Kunal, who's here, he developed a striping feature for SPDK about, I think, a year and a half ago. And we've got cases where we want to do some basic replication and add to that, maybe even do some parity. So I think that's another area that we're going to be looking at over the next year. And then, of course, better performance. So we're always that's why people are using SPDK, right? Like if you didn't care about performance, then you wouldn't be using SPDK. So we're always looking, how do we improve performance? If anybody's been looking at the SPDK mailing list, you'll see a bunch of patches and work that Ben Walker's been doing to improve that. And again, you're going to see some pretty exciting numbers out there. We're talking like 7 to 8 million IOPS on a single Xeon core with the SPDK NVMe driver. It's pretty crazy. And so we're going to continue to be doing work in that area. I think NVMe TCP is probably another one that we're going to be focusing a lot of time on this year. So call to action. Yeah, take advantage. Today and tomorrow there's going to be a ton of talks about SPDK, but also PMDK and Intel vTune amplifier. So, if you see me, you've got any questions about anything, please feel free to pull me aside. Would love to answer your questions. You'll see a lot of the other SPDK core maintainers and developers here who would also be really, happy to answer questions you might have. And join the community. We've got. There's a lot of things to do in SPDK. If you're using it, it may not look like patch contributions. It could be bug submissions. It can even just be asking questions on the mailing list. We've got a lot of people who are now getting answers to questions they have on SPDK by Googling their question, and they find it on our mailing list archives. So that's just another really great way to join the community. So with that, I am going to introduce Mr. Andy Rudolph, who is going to come and give you a similar talk on the Persistent Memory Development Kit.